Well, back with the Softlogix PLC connected to an Arduino Mega. This time I changed the code on the Arduino Mega to also transfer the values of the analog channels. And to one analog channel I added this, which is a voltage divider that has a thermistor on the upper leg and a 10 kilo ohm resistor on the lower leg, and that's a voltage divider. And the thermistor runs inside this little freezer. You see it's taped to the back of the freezer, and this is just a freezer from which I took the electronics from. So the Peltier, the fan, and the heatsink are still intact. So what is controlling it is a couple relays configured as an H bridge, and the Peltier is in the middle common contacts of both relays, and the relays are there so it can change the polarity. And you know, when you change the polarity on a Peltier cell, you can either move heat from inside to the outside, dissipate it through the heatsink. That's a freezer, that's a cooling function. When you reverse the polarity, you're actually taking heat from the outside and move it in. And so that's the cool thing about a Peltier. You can use it for heating. It's a heat pump to move heat in or out directionally, bidirectionally. So a couple transistors, configure a couple NPN transistors with diodes to dissipate the back EMF from the relay coils. And the relay coils, the contacts just drive the Peltier down here. On the back here, I have the Peltier. There's a little mess here, but I'm trying to get a screenshot of it. So that's a Peltier connected to the commons of the relay. So everything is just a prototype. This is just it's not even a final product at all, not by any extent, but you get the idea. So on the ladder I have this little block which takes the analog channel from the Modbus Arduino Mega and multiplies it by 1.0, converting it from integer into floating point, and put it into a real tag. And now the real tag converts, goes into all this math compute functions, which I forgot the name of the equation, Harting or something. But it actually takes some logarithmic equations and cubic values of those and converts that. You can see the absolute zero value here. Converts that from a raw value directly into Celsius. So I have a Celsius here. Let me get that. Oh, get here again. So the main. Go to the main. Okay. So I have the function block here for a PID. And I want you to look into this. So if you hover the mouse over this, you get this CTL.25, and basically this is changing from heating to cooling. So PV minus SP, that's cooling, and SP minus PV, that's heating. So you can switch that on and off by simply toggling that. So this is what this cooling function does. It turns that selection to be cooling, or heating turns it off. So I can select if it's cooling or heating. Right now it's cooling. So I take the temperature coming out of the thermocouple, which is 10.13 Celsius. I have a set point of 10. Now I'm going to change that to, let's say, 15. Right, 15. So that's going to change the output. Right now it's going to start to lower the output because I'm cooling it. I'm calling for higher temp, so no more cooling. So you can see that down here, the output, I have a running cycle timer here of 2.5 seconds. What the process output does is changing the duty on. Duty on is this value here that is a result of multiplying the output times the cycle preset. So it changed the percentage of the duty cycle the output stays on. So you can see I'm cooling here, and you can see the relay. You can hear it clicking now. So output 1 is cooling. Right now I'm not heating, so only one relay is switching. And if I were to look at the trend, see, this is what I changed the set point. See the purple line, the pink line, that's the set point. I changed the set point. Before that it was kind of hovering. This is the green trace, that's the thermocouple. Oh, not thermocouple, the thermistor temperature on inside, and now I increase it, so it's going to start to go up a little bit here. So it needs a little bit of tuning. Right now I have a proportional gain of, I think it's 1 or 10. Oh, it's 1. And the internal gain is 0.2. Typical for heating. You only have PI. There's no differential or derivative. It's only integral and proportional. Pretty much normal for heating. PI only. Anyhow, I probably need to change one of these. I forgot the process KP. But for now, go back to the trace. That's where the process is heading to 15. So it's allowing the thing to heat up. It's running less and less. I could add the output on and off here, so you can see how it changes the duty cycle. So the Peltier stays less time on, just like you expect with a proportional time on function. But that's pretty much this week's project. Thank you for watching.